In the previous class, we learned about the Coulomb's law. Now we will learn another physical entity today, that is electric. Let a charge Q is placed at O and another charge, this Q, is placed at point P with position vector R from O. Now, if this Q charge is removed, then what is left here? We can here say if Q charge is here and this Q charge is at origin, then between these two charges there's a Coulomb force. Now, if this Q charge is removed from this place, then what is left? Physically, we can say nothing is left. If nothing is left, then why again if the Q charge is brought here will experience a force? To answer such question, scientists given another concept, that is of the electric field. Electric field is defined in every point, at every point in this space, and it varies from point to point. This electric field is a vector quantity and its unit is Newton per Coulomb or volt per meter. Newton per Coulomb, if we see this unit, then we can see it is the force experienced by a unit positive test charge. But now, the electric field produced by charge Q at point R is given by vector E equal to 1 by 4 pi epsilon naught Q by R square unit vector R. Unit vector R is the direction along O to P and magnitude is of R. In vector form, we can write this one as 1 by 4 pi epsilon naught Q by R Q R vector. Now employ here the Coulomb's law. That is the force exerted by this charge Q on a charge Q is F equal to 1 by 4 pi epsilon naught product of these two vectors by R square. Direction from origin to P. Now from this equation 1 and equation 2, if we use, we will find electric field is equal to Q times of the force experienced by that charge. So E equal to Q into F. Now if this Q is equal to unity, then we can say electric field is numerically equal to the force exerted by the charge Q. Here, the Q is called the source charge and a small q is called test charge. Now, how we can say that this one is a Q charge? It is the consideration the source charge must remain unaffected from the presence of another charge. Let's say Q. This can be achieved by making Q is negligibly small. So mathematically we can write vector equal to limit Q tends to 0 F by Q. Another important point, electric field at R due to Q is independent of the test charge because the force experienced by test charge is proportional to Q. So the quotient, that is F by Q, does not depend on Q. Electric field due to Q depends on the space coordinate R, and it has a spherical symmetry. For a positive charge, E will be directed radially outward from the charge, and for a negative charge, it will be directed radially inward from the. Here, the direction of electric field for positive charge, see it is the radially outward, and at different point, electric field will be differ. For the negative charge, the direction of electric field is direct radially inward. So we can say electric field is defined at every point in the space. It gives the magnitude and direction of force that a unit positive test charge will experience at that point. It is helpful in dealing with time-dependent electromagnetic phenomena, which we will learn later on. It can be detected only by its effect on the charge. So it is a physical entity. It has independent dynamics. It can transport. Now, a few questions here given for yours. Try to solve these questions. Thank you.